Man's ability to measure the speed of light provides a starting point in calculating the unknowns, astronomy, and other sciences.
Central Flight 551.
Requesting radar landing instructions, over.
Midland Tower to Central Flight 551. Now approaching the zoning area and heading 130. You are now over industrial area. Going low on glide path.
Adjust your rate of descent.
Glide path improving.
Half mile from touchdown. Right on course.
On the glide path.
Approaching end of runway. Now, right on center line. Right on the glide path. Start braking your glide. Take over visually and complete your landing.
One after another, these giant airplanes are brought down safely. Even though fog blankets the land, the revolving antenna sends out radar signals. These signals, or radiations, hit the airplane and are reflected back to these scopes, like echoes, only many times faster. Radar signals travel at the speed of light. Even the short time that it takes these radiations to go to the plane and return can be measured. Since the speed of light is known, the plane's distance from this electronic scope at the airport can be determined. This is an example of the importance of the constant, the speed of light. But how is this important constant discovered? To find out, we must go back 300 years.
It was in 1654 that the first known attempt to measure the speed of light was underway. The work was directed by the famous Italian physicist Galileo. The place, 2 hilltops near the city of Florence. Galileo uses a pendulum to measure time and a lantern with a shutter to provide light for the experiment. On the adjoining hilltop, Galileo's helpers wait for the instant when Galileo will reveal his lantern light. Then the helpers will immediately signal back with their own. Their plan is to discover how long it takes light to travel from one hilltop to the other. Practice signals are exchanged. Galileo inspects the equipment. The lamps are darkened. The moment has come. Galileo gives the signal. Galileo can scarcely believe what he sees. He and his helpers try again. Now there can be little doubt. There is no perceptible interval of time between the signals. Evidently, light travels instantaneously from one place to another. Galileo decides to test the speed of light over greater distances. He realizes that by using a telescope, he can see light many miles away. So he plans another experiment in which he will place his observers on hills many miles apart. Unfortunately, the experiment never takes place because of Galileo's death. During the years 1671 through 1676, another famous astronomer, Olaf Raymer of Denmark, watches the eclipses of the planet Jupiter's satellites. He keeps painstaking logs of the eclipses. Night after night, year after year. Then in September of 1676, before the Academy of Science in Paris, Raymer predicts that on November 9th, the eclipse of Jupiter's first satellite will be seen 10 minutes later than the time computed on the basis of previous eclipses. Accordingly, on November 9th, 1676, at the Royal Observatory in Paris, members of the Academy of Science gather to see if Raymer's prediction will come true. The timer takes his place. The observer is stationed. The eclipse should occur momentarily if Raymer is correct. And then, the eclipse exactly as Raymer predicted. On November 21st, 1676, Raymer appears once again at the Academy. This time, he explains the basis for his prediction. To do this, Raymer demonstrates this apparatus. Raymer explains that this represents the sun, the Earth and its orbit, and this represents Jupiter and its first satellite. When the satellite passes into the shadow of Jupiter, the eclipse occurs. He refers to his logs, the logs on which he has charted the eclipses of Jupiter's first satellites. During the lapse of time between these dates, the Earth moves around the sun in its orbit. As it moves, the distance between the Earth and Jupiter increases. And as time passes, the eclipses of Jupiter's moon appear to be later and later. At the end of 6 months, when the Earth is farthest from Jupiter, the eclipse occurs about 1,000 seconds later than when the Earth and Jupiter are closest. Thus, Raymer has a basis for his prediction. He knows that the diameter of the Earth's orbit around the sun is 186 million miles. He can tell from his observations that it takes about 1,000 seconds more for light from Jupiter to travel this distance than the time it takes to travel this distance. He divides the diameter of the Earth's orbit, 186 million miles, by the time difference of 1,000 seconds, and concludes that the speed of light must be 186,000 miles per second. In arriving at this important conclusion, he has used the telescope, the instrument developed by Galileo. And he has studied Jupiter's satellites first seen by Galileo in the year 1610. Now let's move forward in time almost 200 years to 1849. Armand Fizeau, a French physicist, is about to try a new kind of experiment to find the speed of light. In this experiment, he plans to use this many-toothed wheel. Fizeau uses a shutter principle discovered by Galileo. As Fizeau rotates the wheel, the light is cut into a series of light flashes. The flashes travel to a distant mirror and are reflected back. If after the flash goes out, its return is blocked by a tooth on the wheel, no light can be observed in the telescope. If, however, the wheel rotates the full distance of one slot in the time it takes the light flash to travel to the mirror and back, the light can be seen in the telescope. T, the time it takes for this slot to rotate from one position to the next, is known. D, the distance that the light travels to and from the mirror, is also known. With these data, Fizeau calculates C, the speed of light, is equal to D, the distance, over T, the time. So it is that Fizeau advances the study of light, using his so-called terrestrial experiment. His calculations indicate that the speed of light is 196,000 miles per second. Now the year is 1862. Jean Foucault tries a modification of Fizeau's many-toothed wheel. He substitutes a revolving mirror for the wheel. 17 years later, in 1879, Albert Michelson finds that by shifting Foucault's optical system, he can get a much brighter return reflection over a far greater distance. During much of his life, Michelson continues experimenting with light. This time, he is about to flash a light from Mount Wilson in California to Mount San Antonio, 22 miles away. The plan is to reflect the light back to Mount Wilson. The arc lamp is struck. Here is the beam of light. It is reflected by one face of the Michelson 8-sided mirror to a mirror on Mount San Antonio, 22 miles away. From the mirror on Mount San Antonio, the light reflects back to another face of the 8-sided mirror. Since the mirror is stationary, the light can be seen through the telescope. Now the mirror is rotated. Light is reflected from the rotating mirror to Mount San Antonio and back again to another face of the 8-sided mirror. This time, the mirror has not turned far enough to reflect light to the telescope. The mirror is rotated faster until it revolves exactly 1/8 of a revolution in the time it takes the light flash to reach Mount San Antonio, return, and be seen through the telescope. Michelson discovers the speed with which the mirror must turn in order that the light flash will reach the telescope. In his experiment, Michelson knows the distance from Mount Wilson to Mount San Antonio, and he can measure how fast the mirror is turning. With these facts, Michelson calculates the speed of light to be 186,293 miles per second. Michelson continues experimenting with his optical mechanical measuring apparatus until his death.
In our modern electronic age, scientific precision has become one of our most fundamental needs in determining many constants. In recent years, there have been many studies of the speed of light. Scientists use more modern electronic equipment, such as the microwave cavity resonator. However, all these methods use the same principle as Galileo used, of sending out a pulse and having it reflected back again, and measuring the time for it to travel this distance. C, the speed of light, appears in books or periodicals on modern physical theory. C is universally used as the symbol for the speed of light. C plays a basic role in Einstein's famous equation, E equals mc squared. It is part of the quantum theory pertaining to light. It is used in electrical formulae. And it is fundamental in the study of optics. Through the work of Galileo, Raymer, Fizeau, and Michelson, we have come to know more and more about our environment. Today, scientists use the speed of light as the measuring stick of the universe.